Your host, and I want to start today by asking you to just engage in a little mindfulness exercise with me.
Oh, all right. Are we getting spiritual today?
No, a physical one, actually. I want you to just sit there and feel your shoulders,
Yeah.
feel your head, your arms.
Okay.
Do you feel heavy? Do you feel like something is pushing down on you right now?
Because the reality is, whether you feel it or not, something definitely is.
Right, exactly. We are talking about the invisible force that is quite literally crushing us from every angle, every second of every single day.
And strangely, we are perfectly built to ignore it.
We really are. Today we're talking about pressure.
It is the invisible engine of the modern world. I mean, it moves water, it powers cars, it runs entire industrial plants. But as common as it is, it's surprisingly misunderstood.
Yeah. And to make sure we aren't just blown hot air, pun intended, of
Eh.
course, we're diving into a stack of technical training modules from the Northern and Southern Alberta Institutes of Technology.
The NAIT and SAI modules, right?
Exactly. This is the official curriculum for instrument technicians. So we aren't talking about checking your bicycle tires before Sunday ride. This is industrial grade physics.
It really is. And the mission for this deep dive is to move past that basic idea that pressure is just pumping something up.
Right.
In the world of instrumentation, pressure is a variable that can literally kill you if you get it wrong. We need to understand the physics, the absolute mess of units we use to measure it, and the critical and often dangerous difference between absolute and gauge pressure.
Let's start with the basics. I think if you stop someone on the street and asked, hey, what is pressure? They'd probably say it's how hard you push on something.
Which is close. But in physics, close doesn't count.
No, it doesn't.
The source material starts with a very rigid definition. Pressure is the measure of a force exerted over a specific surface area. It's not just the push itself, it is where the push is happening.
Right. The formula they give is P equals F over A, pressure equals force divided by area. But then the notes make this distinction that, honestly, it confused me at first.
The scalar part.
Yeah. They say force is a vector, but pressure is a scalar.
I love that distinction because it breaks people's brains a little bit.
It sounds like Star Trek technobabble. You know, like the scalar readings are off, Captain.
Yeah.
What does it actually mean in plain English?
Okay, think of it this way. If I get mad and shove you, I am pushing you in a specific direction. Maybe I push you backward or I push you to the left.
Okay.
That is force. It's a vector because it has a direction.
So a shove has a destination.
Exactly. But now imagine you are deep underwater in a submarine.
Okay.
The water outside isn't pushing the submarine left or right or down. It is squeezing the hull from every single possible angle simultaneously.
Right everywhere at once.
That is pressure. It's scalar. It has no net direction. It is just a state of being squeezed.
So if I have really high pressure in a pipe, it's not just trying to push the liquid forward.
No, and that is such a common misconception. The flow moves forward, yes, but the pressure is trying to burst the pipe walls outward in 360 degrees at once.
It's an omnidirectional expansion.
Yes, perfectly said.
To visualize this relationship between force area and pressure, that whole P equals F over A equation, the source gives us a really gnarly example involving an industrial compressor.
This is a great example because the numbers are just startling.
So paint the picture for us. We have an industrial compressor. It weighs 600 kilograms,
Which is about 1,300 pounds.
roughly the weight of a grand piano, or a very large cow.
A very heavy cow, yes.
And this machine is sitting on 4 legs. But the text emphasizes that the support pads on these legs are tiny. Each one is only 6.0 square centimeters.
That's the size of a postage stamp.
So we have a grand piano,
Or the cow.
or the cow, balancing on 4 postage stamps.
Right, and this is where the math of P equals F over A comes in to bite you. You have a huge force, which is the weight divided by a microscopic area.
And when the area gets small, the pressure just explodes.
Exactly.
I actually ran the calculation from the notes. It comes out to roughly 2.45 megapascals.
For the listener, that is an enormous amount of pressure. To put it in perspective, the atmosphere we're sitting in right now is about 0.1 megapascals.
Wow.
So that compressor foot is pushing down with 25 times the crushing power of the atmosphere.
It reminds me of that old physics riddle about shoes.
The stiletto heel.
Yes. You would rather have an elephant step on your foot than a woman wearing a stiletto heel.
It's the exact same physics.
Yeah.
The elephant is incredibly heavy, but his foot is huge. That's a big area.
The pressure gets distributed.
Right. The person in the stiletto might weigh a tenth of the elephant, But all that weight is focused on a tiny microscopic point.
That's high pressure.
That punctures the floor.
And that is why industrial floors crack if you don't use support mats. Okay, so we've got the squeeze. We understand scalar, but we need to talk about the biggest source of pressure in our lives, which the text poetically calls the ocean of air.
I love that visual so much.
Uh-huh.
We tend to think of the air as empty space, right? Like if I wave my hand in front of my face, I'm waving it through nothingness.
But the source reminds us that the atmosphere is actually a physical layer of gas about 50 kilometers thick wrapped around the Earth.
And we are bottom feeders.
Yeah.
We are crawling around on the ocean floor, and that entire 50-kilometer column of air is sitting directly on top of our heads.
And air has mass. It actually weighs something.
It does. It's not heavy compared to water, but when you stack 50 kilometers of it on top of you, it really adds up. That weight creates what we call atmospheric pressure.
The text gives us the standard numbers for this pressure at sea level. And I feel like these are basically the holy grail numbers for technicians.
Oh, they are. You have to memorize these. At sea level, standard pressure is 101.325 kilopascals. That's kPa.
Or for the Americans in the audience who are allergic to the metric system,
14.696 pounds per square inch. Sorry, let's just round it to 14.7.
14.7 pounds on every square inch. That means on the back of my hand there's like, what, 30 or 40 pounds of air pressing down right now?
Easily.
Why isn't my hand being crushed?
Because of what we said earlier. Pressure is scalar. It's not just pushing down on the top of your hand. It's pushing up from the bottom, in from the sides, and critically, your body is pressurized internally to match it.
So I'm pushing back.
You are in perfect equilibrium with the ocean of air.
But this leads to a really interesting history lesson in the notes. But a guy named Torricelli.
Evangelista Torricelli, the 1600s. He wanted to prove this invisible ocean actually existed.
And he did it with an experiment that frankly sounds incredibly dangerous by modern standards. The text actually has a big danger warning box next to it.
Yeah, please do not replicate this. He used mercury.
So describe what he actually did.
He took a long glass tube, closed at one end, and filled it to the brim with mercury. Mercury is incredibly heavy, by the way, about 13 times heavier than water.
Okay.
Then he put his thumb over the open end.
His bare thumb.
His bare thumb.
Yeah.
That's the dangerous part. Mercury is a severe neurotoxin.
Ugh.
But he didn't know that. He puts his thumb over the end, flips the tube upside down, and submerges the open end into a bowl of mercury. Then he takes his thumb away.
Now, intuition says the liquid should just glug, 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 run right out of the tube and into the bowl, right? Gravity should empty the tube.
That is exactly what you'd expect. But it didn't. The mercury dropped a little bit, and then it just stopped.
It just hung there.
It hovered there in the tube, creating a column exactly 760 millimeters tall.
It defied gravity.
It looked like it. But what was actually happening was a balancing act. The atmosphere, that ocean of air we talked about, was pushing down on the surface of the mercury in the bowl.
Oh.
That pressure was squeezing the mercury, forcing it to stay up inside the tube.
So the weight of the air outside the tube was perfectly balancing the weight of the mercury inside the tube.
Exactly. He essentially built a scale. On one side, the entire atmosphere. On the other side, 760 millimeters of mercury.
And this brings me to a section of the notes that I honestly found really frustrating. I call it the unit salad. Because of Torricelli and his tube, we are stuck with this bizarre situation where we measure pressure, which is a force using units of length.
It is messy, isn't it?
It drives me crazy. The source lists Pascal's PSI bar and then randomly millimeters of mercury and inches of water. Why do we do this? Why not just pick one standard unit?
It's the ghosts of history. We're just stuck with them. When an instrument technician says the pressure is 20 inches of water, they aren't trying to be poetic.
Right.
For 100 years, the only reliable way to measure low pressure was to hook a pipe up to a glass U-tube filled with water and literally measure how high the water moved with a wooden ruler.
So when I see inches of water on a modern digital gauge, I'm looking at a digital ghost.
You are. The sensor is completely electronic now, but it's translating the data into ruler inches because that's what the engineers and operators are used to seeing.
The notes actually show a diagram of that U-tube manometer. It's a very simple visual. You push on one side of the U-tube, the liquid goes down, the other side goes up.
And the difference in height is your pressure.
Simple, reliable, and it visualizes the concept perfectly. And the notes give us all the conversions for one standard atmosphere, too.
Right, so one atmosphere is 760 millimeters of mercury.
Or 29.2 inches of mercury.
Or 407.51 inches of water.
Which is huge, by the way, over 30 feet of water.
And finally, in 1.01325 bar, it really is a unit salad.
Okay, so we have the physics, we have the atmosphere, we have the messy units. Now we need to get to the boss fight of this training module, the concept that seems to trip absolutely everyone up.
Absolute versus gauge pressure.
I read this section 3 times, and I have to play devil's advocate here. It feels like a distinction without a difference. I have a tire gauge. It reads 30 CSI. Why do I care about absolute pressure? Why complicate things?
You care because your tire gauge is lying to you.
It's lying.
Well, let's say it's omitting the truth. Think about it. When that gauge is sitting on your kitchen table, completely disconnected from the tire, what does it read?
It reads 0.
But we just established that there is 14.7 psi of atmospheric pressure crushing that gauge on the table right now.
True.
So 0 psi gauge pressure is actually a lie. The gauge is calibrated to ignore the atmosphere entirely. It sets the local atmosphere as its 0 point.
Okay, I follow that. So gauge pressure is just pressure above what the air is already doing.
Exactly. But absolute pressure is the objective truth. It starts at a perfect vacuum. 0 molecules, deep space style. It counts everything.
So the formula in the text is absolute equals gauge plus atmosphere.
Absolute equals gauge plus atmosphere. If you want the truth, you have to add the atmosphere back in.
Okay, I get the math, but I still need to know why this matters in the real world. And the source provides this deep space example that finally made it click for me. I want to walk through this slowly because it's a brilliant thought experiment.
It really is. It isolates the variable perfectly.
So imagine we are on the launch pad at Cape Canaveral. We have a car. We take a tire pressure gauge and check the tire.
Standard day. Atmospheric pressure is roughly 100 kPa, just to keep the math easy.
The gauge reads 210 kPa. That's 210 gauge.
Okay, so the tire is pushing out with 210 kPa more force than the atmosphere is pushing in.
But if we want the absolute pressure, the total amount of air molecules banging around inside that rubber, we add the atmosphere. So 210 plus 100 equals 310 kPa. Absolute.
Right. The true pressure inside is 310.
Now we load the car onto a rocket, we blast off, we leave the atmosphere entirely behind, we are floating in the dead vacuum of space.
So atmospheric pressure is now exactly 0.
We send an astronaut out to check the tire with the exact same gauge. Now the tire is sealed, no air has leaked out, it's the same tire. But what does the gauge read?
This is the moment people get wrong. The gauge reading goes up.
It goes up.
It goes way up.
But there's no more air in the tire.
No, there isn't. But remember, the gauge measures the difference between the inside and the outside. On Earth, the atmosphere was a helper. It was pushing back against the outside of the tire, helping the rubber hold the air in.
Oh, so the atmosphere was squeezing the tire, counteracting the internal pressure?
Exactly. But in space, the helper is gone, the atmosphere has left the chat. Now the tire wall has to hold back the full force of the internal air against a total vacuum.
So the gauge reflects that lack of help.
Yes. The formula is gauge equals absolute minus atmosphere. In space, atmosphere is 0. So the gauge now reads the full absolute pressure. It jumps up and reads 310.
So jump from 210 to 310 just by leaving the planet.
Precisely. And that is why this matters so much for technicians.
Wow.
If you are designing a pressure vessel for a high-altitude plane or a vacuum chamber, and you only look at gauge pressure, you might drastically underestimate the forces trying to rip that vessel apart.
That makes so much sense. The gauge is relative to where you are standing. Absolute is the universal truth.
You nailed it.
Speaking of vacuum, the notes touch on that briefly too. It defines vacuum simply as any pressure less than the local atmosphere.
It's just suction. But again, you have to be careful with the units. You can measure vacuum as gauge vacuum, which is counting down from the atmosphere, so like negative 10 kPa.
Right.
Or you could use absolute counting up from 0. It's the exact same physical state just described from 2 different ends of the ruler.
Right. Now there's one final beast in these notes, figure 11, the closed tank.
Ah, the hydrostatic pressure problem.
This diagram shows a tank with some liquid in the bottom and gas trapped at the top. And it gives us 2 gauge readings that at first glance seem completely contradictory.
It's a classic instrument technician puzzle.
So the gauge at the very top of the tank measuring the gas reads 8 kPa, but the gauge at the very bottom submerged in the liquid reads 155 kPa.
That's a massive difference.
And the question is, how much pressure is the liquid itself creating?
To solve this, you have to visualize it like a stack of pancakes, or maybe a human pyramid makes more sense.
I I like the human pyramid.
Okay, so the gas is the guy standing at the very top of the pyramid.
Yeah.
He weighs 8 units. The liquid is the row of people standing directly underneath him. Now, the people at the bottom gauge, what are they holding up?
They are holding up the liquid people and the gas guy on top.
Exactly. They are carrying the total load. So that 155 kPi reading at the bottom is the sum of the liquid's weight plus the gas pressure pushing down on the liquid.
So if I want to know the weight of just the liquid, just that middle row of the pyramid, I have to subtract the guy on top.
Right. 155, which is the total minus 8 for the gas, equals 147 kPi.
So the liquid alone is generating 147 kPa of hydrostatic pressure.
You got it. It's all additive. The atmosphere pushes the tanks, the gas pushes the liquid pushes the bottom. It's just layers of force all the way down.
It really changes how you look at the world. You aren't just walking through empty space. You're at the bottom of a fluid pileup.
We are under a lot of pressure, literally.
So let's wrap this up. We have covered a lot today. Pressure is scalar. It squeezes. It doesn't shove. P equals F over A, so small heels hurt more.
The atmosphere is heavy at 14.7 CS, and your gauge is completely relative. If you want the truth, you have to use absolute.
I want to leave you with one final thought experiment that connects everything we talked about. The ocean of air and the gauge drift.
Let's hear it.
We know atmospheric pressure drops as you go up in elevation. The notes actually say it drops about 1 kPa for every 90 meters.
Roughly, yes. Or 1 psi for every 2,000 feet.
Right. So imagine you are working on the Burj Khalifa in Dubai, the tallest building in the world. It's over 800 meters tall.
Okay.
You take a highly sensitive pressure gauge. You calibrate it to 0 on the ground floor. It's happy. It reads 0 sig. Then you get in the elevator and ride to the top floor 800 meters up.
I see exactly where you're going with this.
You haven't touched the gauge. It's not connected to a pipe or anything. But what does it read when the elevator doors open?
It would actually read a positive pressure.
It would look like it's broken.
It would look like it drifted. But what actually happened is that the ocean of air got shallower. There is physically less air pushing on the outside of the gauge at the top of the tower than there was at the bottom.
So because the pushback from the atmosphere got weaker, the gauge needle just starts to creep up all by itself.
Exactly. You physically moved your reference point. It is a perfect example of why this isn't just textbook theory. If you don't understand the atmosphere, you can't trust your tools.
And on that note, I think we've applied enough pressure for one day.
I think so too.
Thanks for diving in with us. We'll see you on the next one.